between the two oceans cooling down and the natural global cooling cycle coming in, we're going to see a big dip in the temperatures worldwide during the next 10 to 15 years. The cold cycle is going to take about 20 years to bottom out. We're going to be in an extremely cold period during that time, colder than the 1960s and 50s here in the United States. So it's going to be very cold.
I have David Dilley here. And David, could you tell us a little bit about yourself?
I'm a meteorologist-climatologist. I have about 52 years of experience, and I'm still trying to figure that out because I'm only 30 years old. But I've been in the business a long time. I was a weather officer in the Air Force, then in the National Weather Service. Then when I left, I set up my own company called Global Weather Oscillations. The easiest way to remember it is globalweathercycles.com, globalweathercycles.com. And then one of those icons will get you over to our principal site. What we're going to take a look at today is something that no one is really talking about, the carbon dioxide and climate cycles. They're just talking about today's carbon dioxide values as far as the fossil fuel. You're not going to see this out there anywhere on the web. 78% of the atmospheric gases is nitrogen, of all things. 21% is oxygen. 0.9% is argon. That is 99.99% of the atmospheric gases. Doesn't leave much. That's just about all. But that is what we call dry air. The non-dry air includes the greenhouse gases. It's variable. So now, on the greenhouse gases, how much of it is water vapor? How much of it is carbon dioxide? Well, water vapor is anywhere from 1 to 4% of the atmospheric gases. That's quite a bit. It can be 0% at the Arctic and Antarctic because that's a desert, but it can be all the way up to 4%. So 1 to 4%, we'll say. Carbon dioxide, of all things, it's a trace gas. It's less than 0.05%. That's a lot less than water vapor, less than 0.05%. Now, put it in perspective a little bit more. Let's just look at the greenhouse gases here. And what we see is water vapor. We're going to do the average of it, 2%. That's 20,000 parts per million. Natural carbon dioxide, what I'm going to show you later on in the presentation, is 380 parts per million. Now, NOAA and the IPCC says it's down around 285 parts per million. We're going to show you that's false. So the natural is 0.04% of the atmospheric gases. Fossil fuel, I'm going to show you it's only 35 parts per million. That's 0.004%, 4 1,000ths of 1%. And do you think that can cause climate change? Of course not. We go down to Lake Vostok in the Antarctic, and there we have a very deep lake, frozen. They drilled down 15,588 feet down to the bottom. That's a long ways. That goes down over 500,000 years. That's what happens. So they take core samples, and in the core samples, they figure out how much it is carbon dioxide, what the temperatures are. This is what we kind of figure out on the core samples. But these are approximate. This is what they get from the core samples, an estimate of the temperatures and carbon dioxide during the past 500,000 years. And what we see if we go back, say, 450,000 years, the red line is temperature. So what happens, we came quickly, just in a few thousand years, out of a deep ice age into a interglacial warm period. So you can see the temperatures really slid up. And the ice cores estimate the carbon dioxide to be right around 280 parts per million. Then we slide down out of the warm period, a deep ice age, and the oceans. You can see that the carbon dioxide is actually staying up high there. So if carbon dioxide caused global warming, why did the temperatures drop? It does not make sense. But eventually the carbon dioxide goes down because it's being absorbed by the oceans. The oceans keep absorbing it over the course of 100,000 years, sinks into the ocean. Then when you come up on your next interglacial warm period, 338,000 years ago, the temperature goes up and the carbon dioxide is released from the oceans back into the atmosphere. And you can see the carbon dioxide lags behind the temperature rise. And actually, when you hit the peak of the temperature back 338,000 years ago, the carbon dioxide does not peak out until about 7,000 years later. It takes quite a while for carbon dioxide to peak out. And that one peaked out at 298 parts per million. But look at that temperature then drop quickly into an ice age, and look at the carbon dioxide is at its peak. That's proof right there that carbon dioxide does not cause global warming. So as we come over on the right-hand side of the graphic, this is about 18,000 years ago to 11,000 years ago. We came out of the glacial period. We came out of the glacial period, warmed up quickly. We got up to about 290 parts per million. Then we started to take records in Hawaii in the 1950s. And the instruments there said, wow, all of a sudden now we're up to 412 parts per billion. We've never been that high before. This is what we're going to investigate. What is going on with the glacial periods and also the core samples? This is a graphic of the carbon dioxide. This is the peak of the interglacial warm periods every 120,000 years ago. We're going back 800,000 years. The yellow line is 300 parts per million. And you can see we get the peaks about every 120,000 years. And the closest we came to the 300 parts per million was back about 340,000 years ago. But ever since then, we have never been above 300 parts per million, according to the ice core samples. That is the ice core samples. This graphic really shows it here, where we started to take the instrument readings. And look at that. All of a sudden, way above 300 parts per million, up to 413. So this is what we're going to look at. How do we take the samples? And what could be wrong with the sampling data? Is the rise in carbon dioxide since 1850 natural? Is it anthropogenic, which is fossil fuel and human activity, or is it a combination of both items? Very important. And what we're going to do is we're going to take a look at some major errors in the CO2 measurements. Now, I showed you the graphic where they take ice core samples going way down 15,000 feet or so. And this is a picture of an ice core sample. That's a little, probably only an inch or two wide ice core sample. But that covers a period of 1,000 to 4,000 years. That's a long period, that little ice core sample. In the ice core samples, you have little trapped air bubbles. In the air bubbles, they analyze it, and they can determine to some degree what the temperature was over a 1,000 or 4,000 year period, and how much carbon dioxide in that 1,000 to 4,000 year period. However, the big thing is that's a mean value. That doesn't tell you what the peak was. Not actually, it's a mean value, and people are not talking about that. So we're going to show you some corrections here, because when you take a mean value of anything over a long period of time, 1,000 to 4,000 years, or even 100 years, you eliminate spikes in your data. And this is an example of taking a mean value. Let's say this is somewhere in the United States. This is the average temperatures during the course of the year. January, that's location has an average high temperature 60. In the summer, average high temperature 90, excuse me. And for low temperatures, average of 36, then in the summer about 66. So you have averages of a high and low temperatures. Now, when you take a mean value, you're taking an average or a mean of all the data And what happens, that brings it halfway down between. So that shows that in July, your mean temperature is 78 degrees. The mean. Does that mean you've never been up to 90 or 100 degrees? Of course not. You've eliminated that spike. And that spike is about 17% error. And this is what happens in the ice cores when you're taking values over a course of 1,000 to 4,000 years. So what we're going to do, we're going to add 17% back into the ice core values because that is a big error. The second error is when you drill in the lake, in the ice bed, you drill down the core sample, you cannot use the ice core sample during the period which they call new ice. That's the first 5,000 years of formation. The reason you cannot do that is the trapped air bubbles in the ice is not really trapped yet. It takes 5,000 years for it to get locked into place. So during the first 5,000 years, carbon dioxide in the air bubble leaks back into the atmosphere. It leaks back up into the atmosphere. The research says that you lose about 1.5 parts per million for every 44 feet. That's 688 feet. So that means you lose about 30 parts per million of carbon dioxide back in the atmosphere. That's not being recorded in the ice core samples. What I do in my corrections, we have to add 17% back into the mean value, and we need to add the 30% lost carbon dioxide back into the data also. So what happens when we do that? During the past 425,000 years, the green, that's the peak of the carbon dioxide found in the ice core samples. And like we were talking about, we've never gone above 300 parts per million, very close to reaching it, but never above it. Now let's add the corrections. Let's talk about over on the right-hand side too. This is currently the IPCC and NOAA says that this red, that's all fossil fuel. And we're up to 413 parts per million. That's all fossil fuel, the red. Well, let's take a look at the corrections. First, we're going to add the 17% because it's a mean value. Now look at that. That takes well above the 300 parts per million. And on the right-hand side, now we're going to add the 30 parts per million back into it. And when we add the 30 parts per million back into it, look at what we have. 377 parts per million, 378, 375, 375. We're way up there. And let's add the corrections into the current. And that brings it way up there also, close to 380 parts per million natural. And rest of it is fossil fuel. Not that much. NOAA says the rise has been 100% fossil fuel. It isn't. Since 1850, it is 80% natural. Now, do we have other research that will confirm what I'm saying? Yes, we do. New research came out this about a year ago, and they've been adding papers to it. And this corrects NOAA's calculations of the rise in carbon dioxide since 1850. And this is the journal that it's in, the Radiation Safety Journal, Health Physics Journal. And this is the name of the paper itself. It's a big, long name. We won't go through it. The authors are professors of radiological sciences. They're retired. And that's a big thing, being retired. If you're not retired, if you're at a university, you can't do research like this because of federal grants and everything. You can't do it. You have to wait until you're retired, and then you can do real science. When they were working, they were at the Department of Physics at University of Massachusetts. And it's Ken Scrabble, George Chabot, and Clayton French. This is the journal information here. This is what they found. And this is extremely important. Since 1850, the red here is what NOAA is saying is the increase due to fossil fuel, the red. And they're showing all of that is the increase due to fossil fuel. Now, how do they determine that? Well, we have up on a high mountain in Hawaii, we have a infrared spectrometer. Since 1958, it's been taking measurements of atmospheric carbon dioxide. However, three isotopes, carbon 12, 13, and 14. And what the spectrometer does, it's taking the total of all three, and it's not separating what is natural, what is fossil fuel. There's no separation. So NOAA, because the ice core samples says we've never been above 300 parts per million, NOAA is assuming that the rise above 300 parts per million is all fossil fuel. It's an assumption, is all it is. They're assuming it by trying to take averages. Oh, how much of it is taken back in by the oceans? How much of it is given off the industry? That's all assumptions. Now, what the physicists did, they formulated a formula to determine how much is fossil fuel and how much is natural. They went back, well, all the way back to 1750. And then these red lines is, again, what NOAA says is the increase by fossil fuel. Well, their formula separates the carbon 12, 13, and 14 to determine what is what. And this is their findings. As I switched everything over to green, the green is the natural increase in carbon dioxide all the way up to 1958. Now, remember, right now, this paper going back to 2018 says that the increase has been about from 280 parts per million way up to 408. And NOAA says it is all fossil fuel. This research paper says, no, it is 80% natural, just like what I showed on my formulations, 80% natural, only about 23% industrial. That's not enough to cause climate change. Now, I'm going to show you one last paper that will also verify the findings. And this is using a different method, fossilized plant leaflets. And what they look at is, you can see in this picture, there's little cells in there. They call these stomata cells. That's like the lungs in a human being. So they look at the fossilized plant leaflets, and on the plant leaflets, unlike the ice core samples where you're taking an average over 1,000 to 4,000 years, the fossilized plant leaflets can give you the exact year going back the past 1,000 years. So you can determine each year what is going on. So the stomata cells are like the lungs in a human being or in animals. They found that if a leaflet has a lot of stomata cells, that means you had a lot less carbon dioxide in the air at that time, because you have to have more oxygen power, lung power, to get the carbon dioxide. If it has fewer cells, that means there was a lot of carbon dioxide in the air, so the plant leaflet didn't need as many stomata cells. And the byproduct, big thing about plant life, takes in carbon dioxide, and the beauty of it is the byproduct is oxygen, which we drastically need. So this is what the plant stomata cells show during the past 1,200 years. Back in 800 AD, it says we were way up to 375 parts per million natural carbon dioxide. Then it dipped way down. Then at 1000 AD is 325, then it dipped way down to 230, and it dipped up, down, up, down, up, down, up, down. Then in the year 2010, it was up at 375 parts per million. Well, that's pretty good. But, a lot of scientists, when this came out, they poo-pooed this because they said, it can't go up and down like that. It can't go up and down like that. We've never been above 300 parts per million. That's untrue. Scrabble et al., the physicists, and my data shows you, yes, we're up to around 380 parts per million now, natural. So this puts a picture on this, but gee, let's look at the plant stomata. That could be pretty darn real. And also, if you take a mean value of a plant stomata over the course of 1,000 years, you come out 301 parts per million. Mean value of ice cores over a 1,000-year period, 297 parts per million. pretty darn close to being the same. Now let's take the plant stomata readings of the carbon dioxide, atmospheric carbon dioxide, and what we're going to do is overlay it onto our global warming and cooling cycles during the past 1,200 years. We have had 6 global warming cycles during the past 1,200 years, as noted here in the red. This is back around 850 AD. And then you can see it cools down, then we warm up again, cool down, warm up, cool way down. And 1550 global warming cycle, cool down. 6 global warming cycles. People don't talk about that, but we have had 6 of them. Now we're going to overlay the plant stomata carbon dioxide, atmospheric carbon dioxide. And guess what we see? A perfect fit. The high values in carbon dioxide are on your peak of your global warming cycles. So that brings a lot more credibility into the plant stomata cells for recording carbon dioxide. So putting it all together, what we see is since 1850, NOAA and the IPCC says that the rise in carbon dioxide, atmospheric carbon dioxide, is 100% due to fossil fuel and human activity. The 3 studies I just showed you, the corrections I made on the ice core samples, Scrabel et al., the physicists, and the plant stomata, we all show it's 80% natural rise. Far too little fossil fuel to cause climate change. It is almost all natural. And we're going to just take a quick look again at the 6 global warming cycles since the year 800 AD. Now there's 1, 2, 3, 4, 5, 6. And what we see is when we come off the global warming cycle, this is around about 900 AD, go into a global cooling cycle. The next global cooling cycle begins about 200 years later. The next global cooling cycle begins right here, 230 years later. The next one about 240 years later. Next one, 230 years later. And then here we are today over here on the right. The average is a global cooling cycle coming about every 230 years. And the global cooling cycles last for a good 100, 150 years. So here we are right now. The average for the return of the global cooling cycle is 230 years. The last global cooling cycle began in 1794. You add 230 to that, and we're in the year 2024. Right now, this is 2023. So we should be sliding into a global cooling cycle, natural global cooling cycle. And we have signals that it is beginning. Now, global warming cycles, they begin in the Arctic and the Antarctic. They warm up over the course of 20, 30 years or so. They warm up. And as the Arctic and Antarctic warm up, that means there's less cold air available for the mid-latitudes. So over time, the mid-latitudes warm up. So that's where global warming begins. Then what happens is global cooling also begins at the Arctic and the Antarctic. And what has happened? In 2022, that's just this past year, the spring and summer in the Arctic was the coldest on record. You had that during a global warming cycle? That's a signal that the Arctic is drastically cooling down. In 2021, the Antarctic had the coldest winter on record. So how can you have these 2 records like that if you're not sliding into global cooling? There's more cold air available, and it's going to cool down the mid-latitudes. That is our global cooling cycle. And we're coming into that right now. Winter of 2020 was the 3rd coldest January and February on record, from Alaska through central and northern Canada into Greenland. Antarctica, as I indicated, winter of 2021, coldest on record. Arctic, 2022, coldest spring and summer on record since 1958, and the most Arctic ice extent in 8 to 16 years. And that's what we have, and we can go back on questions. But the real main point is carbon dioxide increase is mainly natural. It is not causing a global warming cycle. It's a natural global warming cycle, and we're sliding back into a natural global cooling cycle.
Very good. Do you have time for a couple of questions?
Sure do.
If you had to make a prediction, what would you think of the cooling between now and 2050? Or do you think it will cool between now and 2050? Are you fairly confident?
Well, actually, we're going to see a pretty good cool down here into January. The whole atmospheric circulation is beginning to change. The La Nina out in the Pacific is now fading. It's going to be gone here by mid to end of January. And we can see changes in the atmospheric circulation going on now. And the colder air in Canada is going to start making its way down more into the United States during late January and February this year. So we do see a drastic change. And what we're going to see really is, through 2050 or so, the IPCC and NOAA says that the oceans are going to rise anywhere from 8 to 26 inches during that time period. I say may raise an inch, may not even raise that much, because we're going into a global cooling cycle now. The poles are cooling down. Pacific Ocean has phases going back to the year 1580. For past 500 years, we've seen these cycles, what we call warm phase and cold phase cycles in the Pacific Ocean. They last for anywhere from about 25 to 40 years. The Pacific has been in a warm phase cycle, 40-year warm cycle, which kind of ties the record going back 500 years. Pacific is sliding into a cold or a cool phase ocean water cycle, and that's going to help to cool down the Arctic, and especially up around Alaska. And the Atlantic Ocean will be going into a cool phase right after 2030 or so. So between the two oceans cooling down and the natural global cooling cycle coming in, we're going to see a big dip in the temperatures worldwide during the next 10 to 15 years. The global warming cycle took about a 20-year period to peak out, warming from about the year 2000 up to about 2021. So it took 20 years to hit the peak. Well, the cold cycle is going to take about 20 years to bottom out also at the coldest. And that's going to be around 2040 or so, or late 2030s. So we're going to be in an extremely cold period during that time, colder than the 1960s and 50s here in the United States. So it's going to be very cold.
Okay, very interesting. Is there any sort of a simple explanation as to what causes that 230-year cycle that you mentioned?
It is. The simple explanation is our glacial periods and interglacial periods that come about every 120,000 years are due to the Earth's path around the sun, where the Earth swings out further away from the sun, and also the tilt of the Earth also changes. And when we swing out the furthest point from the sun, we're really deep into the glacial period. Now, we have shorter cycles of the Earth, Moon, Sun, where they have various cycles where the Earth does swing in a little bit closer to the sun, and also the moon swings in closer to the Earth, and also in certain alignments. It's a gravitational cycle. We call it the electromagnetic gravitational cycles. And everything in the universe, in our bodies, and in the core of the Earth is electromagnetic. So it's all controlled by these cycles of the Earth, Moon, Sun is what happens. And the gravitational cycles, the various cycles, we have one every month, but stronger ones come every 9 years, 18 years. And then we have some stronger cycles going out 72 years and the 220-year cycle for our global warming, global cooling cycles. So it's all these short cycles that come every 230 years is the electromagnetic gravitational cycles. of the Earth, Moon, Sun.
Okay, very good. I have one last question. Just yesterday, I had Malcolm Roberts on here, and he was saying there was a guy named Beck who had some chemical measurements of CO2 levels from the 1800s that were between maybe 400 and 600 parts per million. Do you put any credence into those?
Well, what I'm seeing, we saw that on the plant stomata cells, and I'll even slide back to that one, where the plant stomata cells data was showing around 350 parts per million or 340 parts per million natural back in the 1800s. And a lot of these are still estimates, and it kind of depends where the sample was taken. But I'm sure that Beck took the sample, it was probably at least mid 300s. And here we have NOAA saying we've never been above 300 parts per million. This is all false data. I call what the NOAA is doing and IPCC, their science, that is political science. What we're looking at here today is real science, not political science. There's a huge difference.
Anything else you'd like to share before we go ahead and wrap up?
Well, I think that's pretty much it. One thing is new data out is showing that we've actually been cooling a little bit since during the past 5-6 years. So this is all looking like, yes, we are already going gradually into the global cooling cycle, but we're going to see a more dramatic change in the cooling cycle, and we're starting to see it now. Keep your eyes open next few years. All of a sudden, in a few years, people are going to be saying, wait a minute, what are we doing here? We're down the wrong path. We need to wake up.
Excellent. And then I wanted to make sure just the best places to see your work are globalweathercycles.com and globalweatheroscillations.com. Is that right?
Correct. Globalweathercycles.com. Our principal site is Global Weather Oscillations, but go to Global Weather Cycles, an icon, and it'll take you over to the website. And I do have videos, have a full video on there that discusses what we discussed today, and also the cycles of the Earth, Moon, and Sun.
All right. Well, thanks a lot for taking the time. I really appreciate it. I'll put some of those links in the show description as well. But thank you. We'll talk to you next time.
Thank you very much for having me on.